Hello there. In this lesson, we're going to learn about electrical efficiency and cost. You might have looked around your home and seen different styles of light fixtures, light bulbs. This is one that I recently changed in my home. This here is a compact fluorescent, or CFL, compact fluorescent light bulb. And this one here is an LED, or light emitting diode, right? And so both of them produce light and do the job that they're designed for. But there are reasons to choose one over another, and we're going to look at some of those reasons today. Mostly to do with the amount of energy they use. And of course, as we learned earlier, energy has to come from somewhere. It has to be either like a chemical reaction or comes from burning fossil fuels or nuclear power. And so all of those things have a cost, both as money and also to the environment, and how difficult it is to maintain that amount of energy production. So we're going to look at some of the ways in which electrical energy is quantified, and how efficiency can play a role in our choices. So one term that we need to use in order to compare devices is the amount of energy they use per unit of time. And that term is called power. So power is how fast energy is being used. Power is measured in the unit called the watt. It's named after James Watt, who is a Scottish inventor of the steam engine. And so a couple other units that you might want to know as well is the unit of energy. Energy is measured in joules. Used to be calories, now it's joules. Sometimes it's still calories, depending on your use of it. And the unit of time we're going to use is seconds. So 1 watt is 1 joule of energy per every second, either being produced or being used up. And so that's a way to measure how fast electrical energy is being used. So we can put that into an equation where power equals energy over time. And just like in our chemistry unit when we were doing density relationships, we can make a triangle out of that and help make it a little easier to rearrange. Just make sure you put the energy on top and you're good. So let's try a couple here. It says how much energy is consumed by a 10-watt light bulb in 30 minutes. All right, so we get 10 watts. And we were looking for energy, so we want this guy. So energy equals power times time. The power we have in watts, that's given, but the time is given in minutes. So we need to change that into seconds. So we got 30 minutes, and we know that there are 60 seconds in every minute. So on the side, we would work this out. So I got my calculator here. 30 times 60 equals 1800 seconds. Okay, so now we can use our equation, 10 watts times the 1800 seconds, and that'll give us the amount of energy. So times 10, of course, that's going to be 18000 joules, right? Be the unit of energy. Okay, so let's have a look at this next one here. It says, what is the power usage? So P using of a calculator that consumes 30 joules in 5 seconds. So this time we want the power. That's this guy. So it's going to be E divided by T. So energy divided by time. And we can just put in the 30 joules of energy here and the 5 seconds of time. And so we're on, this is a very short amount of time. So if it uses 30 joules in 5 seconds, that's going to be 6, and the unit of power is watts. So it's a 6 watt calculator. All right, so watts are a very small unit of power, and seconds are a very small unit of time. So when it comes to the energy usage in a home, where an awful lot more energy is being consumed, the units are scaled up so that we can have larger quantities of energy measured. So instead of watts, we use kilowatts, right? So kilowatts, and that means 1,000 watts. So kilowatt equals 1,000 watts. And then hours, of course, that's a lot more seconds. That's 60 minutes times 60 seconds. And so that's 3,600 seconds. That's a lot more time. And so a kilowatt hour is going to be 1,000 times that. So you're up to like over a million or 3 million or so joules of energy. And kilowatt hours is how we are charged for the electricity in our homes. And so we consume much larger amounts of energy than is easily measured with a small unit like watts or joules. And so instead of using joules, they use kilowatt hours to measure how much electrical energy you're consuming. So if you get a chance, if you've seen the electricity bill at your home lying around, or a lot of times it's online now, we get charged for electricity here in Ontario based on when we use it. And so there are times when it's easier to generate electricity, not as many people are using it, and so we don't have to rely on more costly methods. And so these off-peak times, like between 7 at night, 7 in the morning, that's when you'll get charged the least amount of money per kilowatt hour of energy that you use. And then, of course, when everybody turns their stuff on in the morning and in the evening to eat, cook dinner and breakfast, that's when the electricity is going to be the most expensive, more than double there. And then through the day, when people are doing their everyday stuff, it's sort of in between. So depending on the time of day, you'll get charged different amounts of money for the electricity that you used. So to work out the amount of money that you're going to pay, the cost of the electricity that you're going to consume, you need to know the power. And we're going to measure our power in kilowatts. We need to know how long, and we're going to use hours for that. And we're going to need to know the price. And then you can use a price like this guy here, which is cents per kilowatt hour. And that'll give us the amount of money to be charged in cents, right? Because everything else will cancel out. Okay, so let's have a look how that will work out. It says, what is the cost to operate a 2300 watt clothes dryer for 4 hours if the electricity price is 12 cents per kilowatt hour? Okay, so cost equals, so first off, we're going to start off with the power used. So the power here is in watts, but we're going to get charged in kilowatts. So we have to change this into kilowatts. So to do that, you're going to divide by 1,000, right? So 2,300 watts, and we know that there are 1,000 watts in a kilowatt. So if you divide by 1,000, you'll end up with 2.3 kilowatts. Great. So 2.3 kilowatts is the power. Then we're going to multiply it by the amount of time. Because we get charged in kilowatt hours, we're going to leave it as hours, so 4.0 hours. And then we multiply by the price, 12 cents per kilowatt hour. Now to put all this together, 2.3 times 4.0 times 12 is, I get 110.4 cents. 110.4 cents to run the dryer for 4 hours. And you could also change that into dollars if you want, because you know that there are 100 cents in a dollar. And so that would mean it'd be $1.10-ish. Okay, hopefully that helps. So to help you rearrange the cost equation, you can also use a triangle. It's a little bit different because the bottom here is split into 3 spots, but it works the same way. So we're going to use this, this rearrangement to figure out the amount of power of a device that has these components. So to get power, we need to take cost and divide by these two. So power equals cost divided by time times price. A little hint here, make sure you do the time times price first, and then you can divide the cost by whatever value you end up with there. So the cost here was 50 cents. The time is 5 hours, and the price was 12 cents per kilowatt hour. Now it's important to put all these units in as a reminder, just to keep track of everything, and it also is a way to sort of verify the units that you'll end up with. So you see that cents sort of cancels out. Cents divided by cents will divide out. Same thing with hours divided by hours, those divide out. We should end up with some kilowatts when we're done here. I'm going to leave the 50 cents and do the bottom part. So 5 times 12 is 60, I believe. Yeah, 60. And 60 is, what's left here is cents per kilowatt, because the hours divided out. And then 50 divided by 60 should give me, there we are, 0.83. Goes on and on there. And the cents are gone now, so that should just give us kilowatts. There you go. 0.83 kilowatts is what we're looking for. Now, finally, now that we see that the cost of electricity is influenced by how quickly or how much power the devices we use are consuming electricity, efficiency becomes really important because it's going to cost you money, and even if you got lots of money, the effect of having more energy usage has an effect on the environment. So less money spent and also less impact on the environment means that using more efficient devices is always preferable. So efficiency is determined by dividing the amount of energy that goes in, which is the electricity, divided by the amount of energy that comes out, which depends on the load. Must be an O there. Yeah, so you can turn that into a triangle as well if you take this times 100 and move it over to the other side. So the percent efficiency over 100 equals the energy out divided by the energy in. And then you can use it just like you did all your other triangles in rearranging it. Or you can do the mathematical way and just rearrange it like you do in algebra. So here we go, just for a device to give you a little practical explanation of what energy output versus input is. With this toaster, of course, the electricity going in, that's the input. And then the energy that comes out is heat, right? So the heat that comes out is where the energy that the purpose of this load is. Now there may be some other energy that's lost. Clearly 200 joules is being lost somewhere. It might be vibrations. It might be heat that leaks out the side here that doesn't actually go into the toast. And so there's a certain efficiency related to this toaster, and you might be able to find toasters that can get the same job done but consume less energy in doing it. And so that's why an efficiency calculation is helpful. It can help you identify which devices are the most efficient and therefore will use less energy, less money, and less cost to the environment as well. So we'll get back to our original problem here. Which of these light bulbs should we choose? We'll work out the efficiency of both. Both of them produce the same amount of energy, 50 joules of light in a given amount of time. The bulb on the left uses 65 joules, so that's the energy in was 65 on the one on the left, and the one on the right here used 110 joules, right? So let's work it out for both of these. So the percent efficiency equals the energy out is 50 joules. For this one, it was 65 joules of energy was consumed to make that 50 joules of light. And 50 divided by 65 times 100 is roughly 76.9% efficient. That's not bad. So let's compare that with this compact fluorescent one over here. Again, the percent efficiency is the energy out, which is the same 50 joules of light, and the energy in, which was the electricity that was consumed, times 100. And so this time it's 50 divided by 110 and times 100 equals 45.5 4% efficient for the compact fluorescent. So given that the compact fluorescent is less efficient, these ones, the LEDs, tend to last longer as well. The better choice for the environment and for your energy consumption and the cost over the long run is going to be the LEDs. And that's why over the last several years, I've noticed it's hard to even find these anymore. Why would you do that when this technology is getting so much better?